My name is Trevor Buchanan. I am an intern with Agate Institute. During this presentation, I want to show you the findings from my research over the course of this summer's internship. My research was centered on using time series machine learning to predict yield. The project was supervised by my mentor, Sindhuja Sankaran, and assisted by graduate students Loshana and Chamelborn. My project involved the process of using IoT images to predict yield. I primarily focused on two steps of the process. The first was creating a framework to detect reference panels in IoT images that can be used to calculate VIs or vegetation indices. The second involved developing a model that could utilize time series VIs to predict yield. Understanding yield before harvest can be valuable in various ways, depending on the crop type and the occupation of those interested. For example, breeders can use yield predictions during the variety selection process. When breeders are narrowing down viable varieties, knowing yield before harvest can help save money and resources. Growers can also use yield predictions to make informed production and management decisions. IoT stands for Internet of Things. The Internet of Things is a network of devices, vehicles, appliances, and other physical objects that are embedded with sensors, software, and network connectivity. IoT units allow for real-time data insights and proactive alerts. It also allows users to access information from anywhere, at any time, and on any device. And, as needed for our application, it allows for near-constant data flow capabilities for detailed time series datasets. The feature shown on the right is an example of an IoT unit and its hardware used for this project. Here we see an example location where IoT units are collecting data. The cameras have been highlighted in yellow, and the reference panels in blue. We will cover what the reference panels are used for shortly. The cameras used for this project measure near-infrared, or NIR, red, green, and blue bands. When sunlight shines on a healthy, stressed, or dead plant, light bands are reflected in specific ways. For example, in a healthy plant, the reflected light would look something like this. And for a stressed plant, and lastly, for a dead plant. Vegetation index is a metric that uses light sensor data to measure the health of vegetation. There are many different types of VI formulas that prioritize different spectral bands or ratios. For example, here is a very commonly used formula called NDVI, which stands for Normalized Difference Vegetation Index. This formula prioritizes NIR and red bands, which, as we just saw, tend to be appropriate quantifiers for plant health. Using IoT images collected, we can calculate vegetation indices for individual plots. In practice, out in the field, weather and time of day play a major effect in light conditions. So, in order to calculate VI effectively, we need to have a reference for light scale. With a reference, we can scale light bands to be more consistent even with fluctuations in weather and time of day. These images are examples of the drastic difference that time of day, weather, and even equipment malfunctions can cause. We need to detect the reference panel, extract its pixel values, and use the values to normalize the image. This way, the values are less affected by exterior conditions. This process of normalizing pixel values for light consistency is called radiometric correction. On the right is an illustration showing how necessary this step is when processing VI values. In order to use a reference panel, however, either a person or a program needs to detect where the panel is in an image. I took two approaches to this problem. Firstly, image processing. The idea is to isolate the panel by recognizing image patterns and manipulating pixel values. I tried a few different image processing approaches, but none ended up being very successful. Here's a high-level overview of my final image processing approach. Shown is an original IoT image. The first step is cropping the image to a smaller, workable zone. Then, splitting the image into color channels. Then, with each of those colored channels, all of the detection and filtering steps can be done. Here is the red channel with a uniformity mask. Then with contour detection. Then with filtering out noise. Then with an area filter. And finally with a rectangular bounding box. All of which outputs this rectangle telling us where the reference panel is. Now this approach only works on some images. For many images, the result looks like this, where there are many incorrect rectangles. The second approach that I took was to use machine learning. I trained two different models for this task. The first is RoboFlow Object Detection Fast, and the second was YOLO V5M. These models outperformed the image processing approach, making image processing obsolete for this problem. On the left is an example of RoboFlow's detection, and on the right is YOLO's detection. Both models ended up not failing a single test case, but I was only able to test the models on a limited amount of data. To fully understand the performance of these models, more time and data would be needed. Once all the IoT data is processed, the next step is to use the time series VIs, like this NDVI series, to predict yield. At each day in a season, we can use the VIs known from the previous days to predict yield. On the right is the yield prediction for this NDVI series for each day of the year. The blue dot in the graph is the heading date for this example plot. Across both winter and spring seasons, the most accurate prediction date falls about 10 days after the heading date. This is because during this period, plants go from a vegetative state to a reproductive state. To get yield predictions, my program utilizes a variant of an RNN called an LSTM. An RNN is just a neural network that has parts that feed back into itself. I also tested using univariate and multivariate models, where univariate has a single input type and multivariate can have two or more input types. Because of the limited data that I was given for this project, I also utilized the form of a technique called SMOTE, where the distribution of data is leveled out so that the model performs better on less frequently occurring data. Another form of model variation was to use vanilla or stacked LSTMs. The difference between the two is simply that vanilla is a single LSTM layer and stacked is a stack of LSTM layers. These are the best models for each season. For both models, the average percent error at the best prediction date indicates that the predicted yield at that date was on average within 1 bushel per acre of the true yield. Further progress on this project is only limited by lack of data. Additional data would allow for better results and further testing. The results of this project are proof of concept that time series VIs collected by IoT units can be used to predict yield. The idea could also be expanded to other types of crops besides simply wheat. I would like to finish by thanking my mentor Sindhu and grad student associates Chema for agricultural insights, Loshana for her knowledge of machine learning, as well as Warsit for the dataset that I was able to work with. Thank you for listening.